Good morning. Good morning, professors. Today, I would like to present our research outcome on reinforcement of different percent by weights of aluminum oxide on the flexural strength of heat-polymerized acrylic resins. The outlines are as shown. Introduction. Polymetal methacrylate, or PMMA, is the most commonly used material for fabrication of denture bases. The popularity of PMMA is mainly due to its superior properties such as biocompatibility, ease of processing, stability, low cost, and aesthetic properties. However, the inferior properties include low thermal conductivity, high coefficient of thermal expansion, low modulus of elasticity, and brittleness, making the material susceptible to clinical failure. The most common physical property used to assess mechanical properties of denture-based material are impact strength and flexural strength. Several methods have been introduced to strengthen denture-based material, including chemical and mechanical modification. Many materials have been used for the mechanical reinforcement of PMMA. The materials that we will focus on in this particular study is alumina. Aluminum oxide or alumina possesses strong ionic interatomic bonding, high hardness, increased transverse strength, and good thermal properties. However, its disadvantage is that its reinforcement may result in increased surface roughness. Objectives and hypotheses. Our objective is to determine the effect of changing percentage by weight of aluminum oxide particle reinforcement on the flexural strength of heat-polymerized acrylic resin. Our hypothesis is to investigate the effect of percentage by weight of aluminum oxide particle reinforcement on the flexural strength of heat-polymerized acrylic resin. The null hypothesis states that there is no significant difference between the flexural strength of heat-polymerized acrylic resin that resulted from different volumes of filter reinforced. The alternate hypothesis states the opposite. Materials and methods. The material used are as shown. Starting with the specimen preparation. 30 heat-cured acrylic specimens were fabricated. All specimens were divided into 3 groups. 10 specimens are one control group was intact heat-polymerized specimen. 10 specimens are 2.5% by weight aluminum reinforced group, and 10 specimens are 10% by weight aluminum reinforced group. The abbreviations for the 3 experimental and control groups are as shown. Firstly, PMMA powder and alumina particles were pre-weighed into 2.5 and 10% by weight using an electronic weighing machine. Then silane coupling agent MPS was measured using a micropipette according to the Arcos equation. Silane was then used to coat the pre-weighed alumina particle using a microbush and waited to dry for 1 minute. Then mix the pre-weighed aluminum oxide particles with resin polymer powder using a magnetic stirrer. Specimens were prepared using the silicone molds, and pink wax was melted into the mold using glass slides to control the thickness of the wax pieces. The wax pieces were invested in the flask and boiled out at 100 degrees Celsius for 5 minutes. The specimens are then packed and processed according to the manufacturer's instructions. The specimens were removed from the mold, finished, and polished with 320 grit silicon carbide paper with a polishing machine. Finally, the specimens are stored in an incubator at 37 Celsius for 7 days before flexural strength testing. The final specimen size is 65 × 10 × 3 mm, according to ISO 1567. After all specimens were prepared, their flexural strengths were tested. Before testing, the thickness, width, and length of each specimens were examined and put into software using a digital caliper. The flexural strength of specimens was tested by a 3-point bending test using a universal testing machine, Shimasu. The specimens were centered on the device. Supporting wedges were 50 mm apart with a crosshead speed of 5 mm per minute and 100 kg load. Specimens were loaded until fractures occurred. Flexural strength was calculated by the manufacturer's software using the shown formula. After data collection, Chaparral-Wick was used for normality tests. The results show normal distribution, so parametric statistical tests were proceeded. The hypothesis, which compares means of flexural strength between control group 2.5% and 10% by weight, were analyzed using one-way ANOVA. After that, post-hoc Tukey's test was conducted for pairwise comparison. Results. The hypothesis investigates how the percent by weight of aluminum oxide particle reinforced affects the flexural strength of PMA specimens. The percent by weight invested the mean flexural strength of each weight percent were as shown. One way ANOVA determines that there was a significant difference between groups, and post hoc Tukey indicates that the 10% by weight groups was significantly higher than other groups. This graph demonstrates that mean flexural strength increases as the percent by weight of reinforced alumina increases from control to 2.5 to 10%. To summarize, the mean flexural strength of 10% particle reinforcement is significantly higher than that of the control and 2.5 reinforcement. However, the mean flexural strength of 2.5% particle reinforcement is not significantly higher than that of the control group. Therefore, the alternate hypothesis was accepted. Discussion. The increase in flexural strength from addition of aluminum oxide particles can be explained. As alumina exists in several crystalline phases, in elevated temperature, alumina will turn into more stable hexagonal alpha phase. Similar to a study conducted by Lacroix in 2008, the addition of 10% alumina significantly improved the flexural strength in comparison to unreinforced group, and the study by Chaijarino in 2012 also states that 10% weight alumina oxide particle treated with silane led to 23.86% increase in flexural strength compared to untreated specimens. Two factors improve flexural strength of alumina reinforced heat-polymerized acrylic resin. First is the even distribution of the aluminum oxide particles. Second is the treatment of silane coupling agent on the reinforced particles. Coating the particle with silane helps to form a chemical bond between PMMA and aluminum oxide. Silane significantly improves the bond strength of alumina particles to PMMA by decreasing the void formation and increasing the compressive strength, tensile strength, flexural strength, wear resistance, and thermal properties. Conclusion. Increasing the percent by weight of silane-treated alumina reinforcement leads to an improved flexural strength of heat-polymerized acrylic resin, but changes are only significant when added at an adequate amount, which is 10% by weight. The results obtained from this experiment is useful in clinical practice because the 50 to 70 micrometer aluminum oxide particle used can be commonly found in dental setting, as they are used in the process of sandblasting material surfaces. However, other mechanical property, especially surface roughness, should be further investigated because it may affect patient comfort and plaque retention on denture-based surface. Moreover, the use of nano-aluminum oxide particles should be considered, as they claim to have even more superior property than micro-sized alumina particles despite their high costs. Finally, we would like to thank you, our research advisors. Thank you. Hi.
Okay, thank you for your presentation. Anyone have the question you can ask, please?
Any questions from audience? Okay, thank you very much, Ms. Montana, for your wonderful presentation. Okay, so just like I have just one question for you. Just want to ask the idea about your future study. Do you have any aspect would you like to study more or focus on that?
As like I said that even though alumina has many good properties in clinical, but surface roughness is still not tested in our research. So if there is any chance, we would like to test on the surface roughness of alumina to see whether there is any significant importance. Yeah.
And besides the surface roughness, is there any aspect other than that that you would like to study? For example, like a thermal conductivities or water absorption and things.
Maybe we would like to study more on like thermal conductivity of alumina as well, because there's still less research about the thermal conductivity of alumina oxide.
Okay. Does anybody have any questions? Okay.